Hello, welcome to the Introduction to Swim Hydraulics. My name is Mark, and in this presentation we will review the hydraulics component of the US EPA's Stormwater Management Model, or SWMM. By hydraulics we are referring to the flow conditions in the drainage system, that is, the ditches, sewers, creeks, swales, and associated structures like ponds, pumps, orifices, weirs, and so on. The hydraulics in SWMM are governed by the equations for the conservation of mass and momentum, and it is assumed that there is gradually varied unsteady flow. There are three options to solve the hydraulic equations in SWMM, and we will typically want to choose the most complex, that is, dynamic wave routing. One of the options of routing method is steady flow. When this option is selected, a unit hydrograph approach is taken, meaning the hydrograph of direct runoff that results from one unit of excess precipitation is spread uniformly in space and time over a watershed for a given duration. This method assumes that the duration of direct runoff is always the same for uniform intensity storms of the same duration, regardless of the intensity. Although choosing the second hydraulics option, kinematic wave routing, may improve your model stability, it is important to note that there are some limitations of this method. This routing method cannot simulate systems with interconnections or loops, or those that exhibit flow reversals, backwater effects, or surcharging. Also, downstream conditions like tidal gates and diversion structures are assumed to not affect upstream conditions. In addition, pressure flow conditions are not modeled correctly. These limitations may severely limit the situations in which the kinematic wave routing method should be used. In the majority of situations, you will want to choose dynamic wave routing. Dynamic wave routing allows for the modeling of situations where there are branched or loop networks, backwater conditions due to downstream tidal or non-tidal conditions, free surface flow, pressure flow, or surcharge, or even flow reversals. Dynamic wave routing must also be used whenever it is important to represent flow devices such as weirs, orifices, pumps, storage basins, and tide gates. In SWMM hydraulics, the basic differential equations come from the gradually varied, unsteady flow equations for open channels, known as the St. Venant or shallow water equations. This is the momentum equation used to calculate flow in a conduit. The momentum equation may be written in several forms depending on the choice of dependent variables. Using the flow Q and hydraulic head, the momentum equation can be written as it is shown here. One way to think of this is that each term represents a different flow routing method with increasing sophistication. For example, if you have just the first term, you have a steady state solution based on only gravity, area, and change in head. Add the second term, including gravity, area, and the friction slope, and you have a kinematic wave solution. Then if you add the third term based on the flow squared divided by area, you're using the dynamic wave routing method. This is the continuity equation. It is used to solve the hydraulic head for each node at each time step. The head is calculated from the flow rate, time step at the beginning of the simulation, and the node's surface area. The St. Venant or shallow water equations used in SWMM's dynamic wave routine are derived from the momentum equation shown on the previous slide and the continuity equation shown on the current slide. Nodes are the storage elements in SWMM and are used to link together multiple conduits. This image shows examples of different types of nodes in the PCSWMM interface, including junctions, storage units, dividers, and outfalls. Here the nodes are rendered to the default shapes and colors used in PCSWMM. However, they can be changed to any shapes and colors you choose. A few additional points about SWMM nodes. The variables associated with nodes are volume, head, and surface area, as we saw previously in the continuity equation. The primary dependent variable at a node is the hydraulic head, H. This head is assumed to be changing in time but constant throughout any single node. The elevation of the water surface at a node is equal to the invert elevation plus water depth. The volume of the node at any time is equivalent to the water volume contained in all half pipe lengths connected to that node. Junctions are the drainage system nodes where the links join together. Physically, junctions can represent the confluence of natural surface channels, manholes in a sanitary or stormwater sewer system, or pipe connection fittings. In PCSWMM, there's an inflow editor in the junction attributes layer where you can add inflows representing direct, dry weather, or rainfall-derived inflow and infiltration. When the computed water level at a node exceeds the rim elevation, water will be lost from the system. This is referred to as flooding. In the conduit profile shown here, the flooded junctions have been highlighted with red circles. Water can also be allowed to artificially pond on top of a junction and subsequently drain back into that junction if a ponded area is assigned, as highlighted in this slide. Another type of junction is the divider. These are nodes that divert inflows to a specific conduit in a prescribed manner. They are only active under kinematic wave routing and are treated as regular junctions when the dynamic wave routing option is selected. A storage unit is a specific type of node that provides storage volume. It can represent a catch basin, a lake, or a storage of any size in between. The volumetric properties of a storage node are described by a function or table of surface area versus height. Infiltration can be modeled for the storage node by assigning it a seepage rate. In the treatment editor, storage nodes can also be assigned treatment expressions for various pollutants. This slide outlines the mathematical concepts underlying the momentum and continuity equations. The continuity equation is solved at the nodes and the momentum equation is solved at the midpoint of the links. This illustration shows how the surface area changes depending on the configuration around the node. The surface area is computed for every time step at every node. For more background information, see page 599 of the SWM User's Guide PDF. 5 different hydraulic conditions or situations can be described for every link between two nodes. The amount of surface area associated with the node depends on the hydraulic situation. In the normal case, labeled 1 in the slide, flow is computed from the motion equation. Half of the surface area is assigned from each node. When there is a critical depth downstream, as in diagram 2, the lesser of critical or normal depth downstream is used, and all surface area is assigned to the upstream node. In number 3, there is critical depth upstream, and critical depth is used. All surface area is assigned to the downstream node. In number 4, flow computed exceeds flow at critical depth, so the flow is set to normal value. Half of the surface area is assigned from each node. When there is a dry pipe, as in number 5, flow is set to 0. If any surface area exists, it is assigned to the downstream node. In SWM 5, conduits are pipes or channels that connect one node to another. Most types of open and closed channels can be represented. The principal input parameters for SWM conduits are inlet and outlet nodes, offset height, length, roughness, and cross-sectional geometry. Optionally, you can also assign entrance and exit losses or flap gates to the conduit. The cross-sectional shapes for conduits can be selected from a variety of standard open and closed geometries, as shown here. A large library of culvert codes can be chosen from in PCSWM by opening the culvert editor in the Attributes panel of a conduit. SWM conduits representing culverts can model inlet and outlet control, super and subcritical transitions, as well as surcharged and reverse flow, as long as the default routing option is selected, that is, dynamic wave routing. If an irregular channel cross-section geometry is assigned to your conduit, you can enter in your own transect data, including overbank information. In each conduit, SWM uses the Manning equation to express the relationship between Q, the flow rate, A, the cross-sectional area, R, the hydraulic radius, S, the slope, and N, the Manning's roughness coefficient. The slope S is interpreted as either the conduit slope or the friction slope, depending on the flow routing method chosen. A conduit does not have to be assigned a force main shape in order for it to become pressurized. Any of the closed cross-section shapes can potentially pressurize and thus function as force mains that use the Manning's equation to compute friction losses. Either the Darcy-Weisbach formula or the Hazen-Williams formula can be chosen under the Dynamic Wave tab in the simulation options. The flow conveyed through the links and nodes is ultimately discharged to an outfall, the point beyond which we are not concerned with the water, at least for the purposes of that model. Every SWM model must have at least one outfall before it can be run. One restriction is that only a single link can be connected to an outfall. A flap gate can be added to the outfall to prevent water from flowing from that outfall back into your model. An outfall can be thought of as a boundary condition where the water surface elevation at that point is one of the following: a fixed value, a time series value, or based on a table of tide elevation versus time of day. Alternatively, the outfall can be assumed to be either a free or normal type. A free outfall stage is determined by the minimum of critical flow depth and normal flow depth in the connecting conduit, whereas a normal outfall stage is based on the normal flow depth in the connecting conduit. Short conduits and weirs are known to cause model stability problems and can be replaced by an equivalent pipe length. This process involves the following steps. First, the flow equation for the element is set equal to that for an equivalent pipe. Thus, the head losses in the element and its equivalent pipe are the same. Then the length of the equivalent pipe is computed using the numerical stability equation. The Manning's end value is then computed. SWM 5 can automatically adjust short pipes. However, it is almost always preferable to address instabilities by reducing the time step when possible, rather than using this equivalent pipe method. This is because equivalent pipes will not provide the same storage volume as those they are replacing. SWM links can be used to represent various control structures such as weirs, orifices, and pumps. Weirs can be used to model outlet and diversion structures. They may be used to provide relief to the sanitary system during periods of storm runoff. Weirs are located in manholes, along the sides of channels, or within storage units. They can be one of four types: transverse, side flow, V-notch, or trapezoidal. Flapgate and end contractions for weirs are optional. This image shows some examples of the various types of real-world structures we are representing with weir links in SWM. This equation shows how the flow over a weir is calculated from the discharge coefficient, weir length, driving head, approach velocity, and weir exponent. A series of nodes can be connected by weir links to model various types of treatment trains, as shown in this sketch. In SWM, orifice links are used to model outlet and diversion structures. In the real world, orifices are typically located in manholes or within storage units. For example, they may be used to divert sanitary wastewater out of the stormwater system during dry weather periods and restrict the entry of stormwater into the sanitary interceptors during periods of runoff. Some of the options for orifice modeling include side outlet or bottom outlet and circular or rectangular opening. A flap gate can be assigned to prevent backflow through the orifice. The basic orifice equation shows how the flow through an orifice is calculated from the discharge coefficient, cross-sectional area of the orifice, gravitational acceleration, and the hydraulic head on the orifice. The discharge coefficient is a function of the type of opening and the length of the orifice tube. A few additional notes on orifices. Reverse flow can be modeled through the orifice as long as you're using the dynamic wave routing option. An orifice link can only be attached to a storage unit node if you are not using the dynamic wave routing option. Control rules can be used to adjust the orifice opening. This can be useful when modeling a reservoir with controlled gates, for example. Energy loss from the optional flap gates is calculated, same as it would be for a weir. As mentioned earlier, there are head losses associated with flap gates. Often weirs, or orifices, are installed with a tide gate at points of overflow into receiving waters. Flow across the weir is restricted by the tide gate, which may be partially closed at times. This is accounted for by reducing the effective driving head across the weir according to an empirical factor, where h is the previously computed head before the correction for flap gate, and v is the velocity of flow in the upstream conduit. Another type of link in SWM is the pump. Pumps are used to lift water to higher elevations. For these links, there's a pump curve relationship between flow and inlet and/or outlet conditions. Control rules can be used to turn pumps on or off. No reverse flow is allowed through a pump link. This slide summarizes the four types of pumps that can be used in SWM. More detailed information on these four options is available on page 60 of the User's Guide to SWM. Outlet links are flow control devices that are typically used to control outflows from storage nodes in SWM models. They are used to model special head-discharge relationships that cannot be characterized by pumps, orifices, or weirs. Outlet links are also often used in dual drainage models where they connect the minor system, that is the storm sewer pipes, to the major system or overland flow paths. In this case, the inlet capacity of the catch basin would be described by a rating curve assigned to the outlet link. An outlet link can also have a flap gate that restricts flow to only one direction. A SWM model is usually numerically stable when the following inequalities are met. This is recognized as a form of the Courant condition, in which the time step is limited to the time required by a dynamic wave to propagate the length of a conduit. You may also recognize this equation as the Froude number equal to 1. It may be a good idea to identify the shortest conduit in your model and determine the routing time step required for that conduit in order to help prevent major instabilities. This concludes the SWM hydraulics overview. For more information on the principles discussed, please consult the User's Guide to SWM.